Good morning to all. My name is M. Srinivas. I'm Department of Computer Science, National Institute of Technology, Varangal. So my paper title is the Direct Disease Classification based on the Spatial Transformer Network and Squeezing and Excitation Block. So in this main thing is we need to identify the different classes of the direct diseases such as the pneumonia, hernia, and anemia, etc. So that is significant in the global health concerns. So which is available currently. The traditional diagnostic methods rely on the manual interpretation of the medical diagnosis and medical image scans. So maybe it will be leads to the potential to the some errors. So to avoid that kind of issues, we need to propose the some here we are proposing the deep learning based model that is called the ThyreXNet for classification of the Thyrex different classes diseases on medical imaging data. So it is a multi-label image classification problem. So in this multiple classes are available. So main motivation of this one is the medical impact. So addressing the significant global health concerns posed by the thyroid disease of the different classes. So that is the one thing. And next one is the diagnosis challenge to overcome the limitation of the human interpretation and methods to leads to the some errors to avoid the errors. And instead of that one, we can do the automation kind of thing. And third one is the potential effect impact on that saving the lives of the persons and reducing the healthcare cost to you and awaiting the burden on healthcare system through the automatic detection mechanism. So based on this, it is motivated further this problem statement. So existing models. So one of the existing method is called a dual branch network for diagnosis of the Thyroid disease from chest X-rays. So in this framework, they utilize the dual branch architecture kind of thing. So one is used for the feature extraction on both lung regions and chest X-ray kind of thing. So both the used in this case and extract the feature representation. For lung region extraction, they use the one of the deep learning model is called the unit model. So it is one of the segmentation techniques to segment the lung regions and extract the feature representations. And another one is they use LXNet model, that is a CNN based model, convolution neural network based model on chest X-rays. So it will be extract the discriminant feature representation, means it will give the better feature representations. And this concatenated both CNN based feature representation and this segmented based feature representation concatenated feature vector used for the classification of the Thyrex disease classification. So another kind of related product is the discriminate feature learning for thyroid disease classification chest X-ray images. So two branch design for the dual purpose feature learning mechanism they use to identify the disease specific features. So in this case, they will use the enhance the semantic relationship between. So for that, they use the one of the deep learning model is called the dense net 121 model. So in this total number of convolutions layers are the 121 layers they use to extract the discriminate feature representations. So these two are the projectors are related in this presentation. Next one is the dataset description. So in this proposed model, we are using the one of the standard dataset that is called the NIH chest X-ray 14 dataset. So it is one of the large collection of the chest X-ray images dataset. So all are X-ray images kind of thing. So it is collected from the National Institute of Health Organization. Simply they will call as NIH. So it's one of the dataset. So in this, how many different thyroid classes is there means 14 different thyroid disease classes are available. Along with that one more class is added, no finding. If the any one of the class is not identified, then by default, no finding class will be detected. So total 15 classes are available in this data set. So where I will collected this data set is collected from the Kaggle, one of the repository is the one of the huge repository nowadays. So that is collected from the Kaggle. So here I'm showing the each class wise how many samples are available for our implementation our problem statement. So total 15 classes is there, different variation of the classes, different number of images available for the in this data set. So here I'm showing the some of the sample images of the different classes of the Thyrex disease. So like mass, nodal pneumonia, pneumonia thorax, infiltration, effusion, like this different class of the few of the samples I'm showing in this slide that is related to the Thyrex disease. So this is my proposed model. In this model, we use the three specific blocks introduced in this proposed model. So initially, how the image size of 384 plus 384 is there. So in this, initially we can use the one of the STN network model you are using. So that is we are introducing one proposed block. Another one is the convex block you are using in this case. So next SE layer squeezing excitation block used along with the convex block. So like this, we have the some consecutive blocks using in this case combination of the freezing layer and convex block and downsampling. So after this consecutive layers, then we are giving to the global average pooling. So it is do the pooling kind of thing, downsampling in the input values. Then after that, you can use the linear layer to the classification kind of thing. So for giving it a sample, it will be classified as the different direct net classes, disease classes of 15 categories. So next, I want to discuss about the each and every block which we introduce in this proposed model. So first one is the STN network, that is called the spatial transformer network. So in this, we can extract the spatial information from the our input image data. So for that, we have the three specific components is there. One is the localization net, and another is the grid generator net, another one is the sampler net. So here in these three components, what we'll do, localization networks, it will be apply the convolution layers on that input image. So that will be generate the discriminate feature representations on generated from the input image. So that generated discriminate feature representations are fed into the grid generator. So that vectors will be fed the grid generator to create the sample grid. So once the sample grid is generated, and which is the virtual image is there, these two feature maps is feed into the sampler. So the feature map and which is generated from the localization network and sampling grid, both are feed into the sampler. So which samples the input image and grid points to produce the final output of the image. So this is happening in the spatial transformation network. So in this case, spatial information will be extracted. Next, I included one more block is the convex block. So it is a convolution model mainly inspired by the vision transformer mechanism. So in it is mainly used to improve the performance of the proposed model due to the in number of parameters are reduced with help of the depth-wise convolution layers used instead of the normal convolution layers. So depth-wise convolutions, what will happen? It will be reduced the follow the channel. Kind of attention kind of thing. So that will be reduce the number of parameters compared to the normal convolution kind of thing. Means each filter contains the each channel contains each filter only. So because of that one, number of parameters will be reduced and computation class will be reduced. And next, along with the previous what we discussed, the convex block, and along with this one, we are using the squeezing and excitation blocks kind of thing. So it is mainly used for the follow the channels layering kind of thing. And in this mainly consists of two parts is there. One is the squeezing part, another one is the excitation part. Okay, so in this we can extract the squeezing part, we can extract the channel wise feature representation. So that will give the singular value per channel. So it will maintain the channel wise information along with the spatial information previously extracted. So this will be reduce the number of parameters also when you are using the channel wise information. And excitation operation is a fully connected layer kind of thing. So which are the channel wise information extracted, then given to this exciting block. So that will be learn the weights which are the generated from the feature representations. So that learn weights will be helpful for getting the better improvement in the accuracy, and it will be reduce the computational time also. So this is another block we are introducing our proposed model. So to evaluate our results, we are using the one of the evaluation metric is called the AUC ROC. So that is the area under curve or receiver operating characteristics. That is simply form we can call as the AUC ROC. So it is one of the standard performance metrics used for the classification problems. So in the ROC curve, the true positive rate is plotted against the false positive rate at various threshold settings. So based on that, we can analyze how the accuracy will be generated. So AUC ROC represents the area under this curve, and it provides the aggregate in the measure of the performance across the all possible classification thresholds. So true positive rate is nothing but the true positive by true positive plus false negative, and false positive is nothing but false positive plus true negative. So here different parameters we are using. One is the batch size, it's 16, and maximum number of epochs are 20, and learning rate parameter is 0.001, and we are using the loss function as a binary cross entropy loss, and optimizer is the Adam optimizer we are using in this case. These are the training parameters we can set. So in experiment results, our proposed model compare with the all other state of art methods, and here we are projecting the each class wise results. Okay, so among the all classes, we can calculate the mean kind of the performance results. So compared to the state of art results, our proposed model is giving the 0.83 accuracy of this one. So this is my performance results, and this is the area under curve we are showing in this case. So each class wise area under curve we are showing. And finally, we are achieving the mean accuracy of 0.83 of on NIH chest X-ray 14 dataset. So in this, we are incorporating the spatial transformation network to extract the spatial information, and with the we are using the squeezing and extraction block. We maintain the channel mechanism to reduce the number of parameters and improve the accuracy of the our proposed model. And future work, we want to focusing on the segmentation task to extract the more information region related kind of thing along with this classification. So it will give the better accuracy results kind of thing. So next here I'm predicting the references which are included in our proposed paper. So these are the some of the references you are projected here. And thank you for your presentation. So any doubts you can ask.